So I'll begin there. Okay, that was me again. So let's move ahead. Well, this is, of course, what we're really talking about is not energy efficiency only, but energy efficiency is part of the developing industrial processes. I think this has been said in almost exactly these words in some of the panel discussions this morning. We're interested in decarbonizing the industry, so we're interested in making it resource efficient, which involves energy efficiency, but not only. And we're also interested in carbon lean production, and that means many things. Energy efficient processes, thinking about carbon capture and storage, or maybe even more reuse. Electrification, important, particularly if the electric power sector decarbonizes as well, which we already see happening. Which means, of course, we can use energy efficiency or energy efficient processes or sub-processes which have electricity as a driving force. We have lots of system issues. Can we reuse and recycle energy within a process? Can we co-locate industrial processes so that they can exchange energy streams with each other in a systematic and structured way? We have introducing renewable energy sources, but since they're limited, we would like to use them efficiently. And we also have, our profile is in fact a circular economy, so we're also talking about recycled feedstock, and that also needs to be done efficiently. So basically, all of these things are very important for the main heading there, and energy efficiency is strategically important for all of those issues. So that was an introduction. These are types of curves which are shown often. This is just one of many from the IEA's energy technology perspectives. This is showing basically what needs to happen to make the difference between what they call 6DS, so the 6-degree scenario, which is the one we don't want to think about. That's the one which is basically disaster or business as usual. It's nasty to think of business as usual leading to disaster, but that's the consensus. And then way down there, the 2-degree scenario, or the 1.5 or sub-2. But the difference between those two, you can see the light blue at the bottom there is basically the projected contribution of energy efficiency. So energy efficiency is big stuff, is the main message there. And energy efficiency, of course, keeps the energy bills down if you're an energy user, but it also does many other things, and there's a lot of discussion now about so-called non-energy benefits related to energy efficiency. And you can see there's job creation, enhanced energy security, we're reducing burdens on infrastructure, of course reducing greenhouse gas emissions, which is a major driver, at least in these large energy-intensive industry. So basically, energy efficiency should get a more important place than it does. So what do we mean? Energy efficiency means all of these things, and they come in their relative importance and their scope, where they kick in on the time scale differs. But you can see there right down at the bottom what we call housekeeping, and that's what maybe first of it. I think most people in industry right now are very busy with the energy auditing, writing their reports, which are due in a few days, and quite a lot of that is about housekeeping. It's about collecting data. It's about good maintenance. It's what I sometimes call the duct tape level, or the 2% stuff. So, turn off stuff when it's not used, improve insulation, reduce waste, and so on. There is, of course, a lot of research goes into energy management, which is to develop the tools to keep track of all this. But that's not the focus of the research we do at Chalmers to any great extent. Control systems, of course, important. Making them work. Variable speed drives, that also kicks in. Predictive maintenance is very important. Don't stop something until you have to better follow up so that you can make those decisions in a better way. There's a lot of operability issues there, so basically try to dig away to move the process so that you can squeeze as much out of it as you can. And that's a lot about understanding control as well. We have some research into that at Chalmers, but I won't talk about it too much. Improved unit operations, that's what a lot of this morning's discussion has been about, essentially. So it's or part of it. And I will reduce that to saying that's not making changes to processes. It's with exchanging one piece of old equipment with something new and better. Compact heat exchangers extract a little more heat out of an effluent stream, for example. Inefficient pipes should be changed, waste heat recovery boilers, and so on. Moving closer towards the research we do, we come into the next, which is my own pet subject, to quote Anders, process integration. That's where we begin to take a step back and look at all of the unit operations and how they work and interact together. So there we're getting a little closer to system design or process design. That's where we're talking about recovering heat, reusing heat in adjacent part of a process or a different process or something across the road in the same plant. That's what we call site-wide. Process intensification comes in there. We have some work going on at Chalmers there. I won't discuss it that much, but that's making several unit operations occur in one single piece of equipment. And finally, the innovative design, and that's, of course, the long term. And that's all of these, introducing combined heat and power. Heat pumping, there's a lot of work to be done there. Electrification has a lot of potential, which could make major changes to the way we design processes. Separation, membranes, Anne-Sophie was there she is. Sweden's membrane expert, or one of them. Site-wide optimization, so avoiding sub-optimization, eco-industrial parks, and the big picture, energy exchanging energy streams with regional energy systems in some way or another. So that's the big picture. What we do mainly in the energy efficiency at Chalmers is, of course, process integration. So we're looking industrial and how can we identify opportunities for doing some of these things. And process integration, many definitions there, but there's an easy one. So it's about analyzing and identifying opportunities to maximize use of energy, water, or feedstock. Mostly by looking at interactions between system parts, not looking at single operations, but how they interact. And heat integration is one of those, and that is very much about how we can, in a systematic, structured way, recover heat from heat sources and reuse them in heat sinks within a process. And pinch technology, which is something we work with a lot, is a set of tools for doing that, and it's very useful for setting targets. If we're trying to make something, to improve something, it's always good to know how good you could possibly be in an ideal world, and that pinch technology is very good for that. It's also good for guiding how to actually proceed when we've set those targets. You can see there, those are some typical savings. You can see they're all somewhere around 20%, so there is a lot of potential for just by improving energy efficiency. This is also important. It's a little small, unfortunately, but this is the same message, the time. So if we're talking about developing processes over time, we have, I don't know, I never dare try and use these, but there we go. No, it doesn't really reach that far. But this one was essentially about, this is housekeeping, basically, if we think about process integration. So that's improving. That's not even about housekeeping, it's about auditing. It's about tracking targets and how well we're doing. And then we can begin to think about how we could improve an existing process, how we could implement new processes or new sub-processes, biorefineries at the same site. And all the way up here we can think about completely new industrial complexes, which are integrated and producing a whole new portfolio of goods and products in a very efficient and integrated way. So we've got the whole spectrum there. Talking about policy, This is also time and energy efficiency. And if we look at least the big processes, oil industry, petrochemical, if we look at how efficient, if we plot that over time, we see that there's the housekeeping, the tinkering, the duct tape. And then suddenly it's time they have their major overhaul every 5-6 years. And then there's an opportunity. Sometimes it happens, sometimes it doesn't, to make a major change. And then that's online, and then the next stop is in 6 years, and so we continue on. The interesting thing about policy is that policy is usually about encouraging this kind of behavior. It's very rarely about encouraging this kind of behavior. And you can see also, when we're talking about time frames, you can see we're talking about, just because of these long cycle times, petrochemicals, complexes can be around for up to 50, or Stenungssund's been in existence for more than 50 years. So you can see typical time frames here are 5 years, 10 years, 20 years. So major challenges in terms of transforming existing industry. Okay, a little more about the role of process integration in strategic energy decision-making, energy-related decision-making. We've all talked about the expectation that at some point the CO2 prices are going to go up, and lots of unknowns about energy prices. This, of course, is gathering momentum for creating conditions for making some fairly major strategic decisions, and thinking about how things are going to evolve over time, and thinking about, well, if investments now must be flexible because we expect the boundary conditions, the outside world, to change pretty fast. So some things we'll be doing at Chalmers. You can see at the top there, lots of cooperation with lots of major energy stakeholders. I forgot Stora Enso there, sorry about that. Despite your fantastic introduction, I forgot your logo type. But lots of work, both with research institutes, industry, academic partners in Sweden, international academic partners, and also we work together with the IEA umbrella organization, see if I get this right, Tori, Industrial Energy Related Technologies and Systems. Did I get that right? Okay, I'm on track. A few examples from Stenungsund. Typical chemical complex, plastics, both PVCs, polyethylene, specialty chemicals, also some work with fuels, industrial gases. Well, I won't dare say nothing special about them. Of course, there's lots of things special about them, but they're a typical complex in many respects. Of course, the major driver behind this type of complex is that in the middle, we have right there, we have a big cracker plant taking in primarily fossil feedstock, subjecting it to high temperature, and cracking it and sending out some constituent, ethylene and propylene, some hydrogen and other gases which are sold to all of these plants around them, who further transform them into intermediates or final products. And of course, so exchanging and cooperation with material flows, that's the business idea of this kind of complex. If we look at this just as a single site, we see that they're emitting about 1 million tons per year of CO2. That puts them in the top 10. If we consider them as just one point source, that puts them on the top 10 emitters in Sweden. So, of course, lots of interest in energy efficiency related to reducing CO2. We've done a lot of work with energy efficiency, and this could just as an example, some numbers to show the importance and the potential of taking a step back and a wide system boundary perspective. So if we look at those 6 plants together, currently they're firing 122, or they're consuming 122 megawatts of hot utility, which is produced in boilers. And we could ask ourselves 2 questions about that. The first one is, if we looked at each of those single plants and try and assume that they improve their efficiency and sum up the efficiency or the reduction of energy usage, what would happen? What happens if we take the big picture and assume they were just one big plant free to exchange and reuse and recover heat freely? We've used pinch analysis. I won't explain that very much. It is very much about understanding temperature scales and about taking an inventory of of streams which need to be cooled, streams which need to be heated, and putting together that information in aggregated curves. And the beauty with that is that actually allows us in a structured way to understand what we call here this overlap. This is where heat is being released on an aggregate level. This is where it's needed. If we overlap them, that gives us a target for how much we could recover and what's the minimum we need to supply externally and how much we need to cool. So lots of information available if we do that. If we do that at Stenungsund, we see that from 122, if each plant does its homework individually, they could reduce their combined usage to 77. So they could save 45 megawatts. If they are considered just as a single total site, we can in fact see that they don't need to fire boilers at all. So in theory, just the excess heat from some cracker ovens and so on, which must occur anyway, is enough to keep the whole site running. Doing this would require reshuffling around, making some major changes to all of the processes. Doing it this way is only about, well, not only, we'll come back to this in a second, but it is only about exchanging heat in a more efficient way. There is no, achieving this target means nothing. There is no requirement that you have to rebuild or redesign or modify any individual processes at all. So that's showing the scope of taking a broad approach. Of course, lots of things need to be done in practice. We need to replace steam lines with circulating hot water. There are lots of issues there. We need to harmonize steam levels. Of course, the 6 plants have been built historically as separate entities. Then there's been no thoughts about harmonizing steam levels, so that's something to be doing. We need to rethink what steam levels we actually supply heat. And also that we have a lot of process off gases used as fuel. We can also maybe need to think about shifting that from one plant to another, so it's fired in the best place. But we have tools to do that. Of course, lots of challenges that the infrastructure isn't there to do that. There is, of course, the issue of if we're going to do things together, then energy efficiency has to pop up high on the agenda, not only for one company, but for several at the same time, with the willingness to collaborate. And that's, of course, many ifs. But if we work on, of course, the one thing is identifying cost-efficient ways to do that. And there's the kind of solution we can come up with. So there's a lot of work need to do to model that, to come up with specific solutions. Lots of work to do also in seeing, okay, could we start slowly and build up? So this is probably about as far as you could go, and this is at least realistic. You can see there. Industry, the partners tried hard to convince themselves and to convince us that that wasn't a realistic number, but in the end they gave up and said, no, it's probably is fairly cost or reasonable to think about this in practice, and even in a business perspective. This is also something which we talk a lot about now. We talked about reusing excess heat internally. That's one option. Other options which need to be compared. So this is about transforming industry. CCS is another way of using excess heat. So it doesn't matter if it's CCS or CCU, but capturing the CO2 usually requires heat. That's another competing way of using heat. Low temperature technology for producing electric power. Organic Rankine cycle, for example, is another. Drying wet biomass to use as a feedstock for a biorefinery is another. Exporting to a regional energy system is yet another. And we need to tackle all of this in a systematic way. That's the main issue there. We've had a number of projects working along these lines. This is maybe an overview. coming close to the end here. This is an overview of what we're doing in our profile. So this has been the block of this morning, the enabling unit operations and processes. We talked about there. This is more what I've been talking about, process synthesis and design for resource efficiency. We haven't talked too much about the resources, although Göran is there. And of course, we also need, and this is something which we also need to work a lot together, the systems analysis. Matthias will be talking about that in a minute, about the technical, economic, and environmental assessment of all of these options. So a few more things today to say how we work together. There's an example, thermal recycling of both plastics and low-grade biomass to be used as a feedstock for producing intermediates. And these are all the things we need. We need process modeling, we need process simulation. So we need a lot of input from the people who know about the technologies, process integration studies. That's our own work primarily. We do that. Greenhouse gas evaluation, we do that ourselves, but we also need a lot of help and input from people who are good at, for example, LCA studies, so we don't completely lose track. So this is example, I think Henrik showed a similar slide. So this is very much, and there's a lot of interesting work to be done here about combining the energy efficiency world with the resource efficiency world and the biorefinery world, particularly if we see gasification maybe got going as just an idea for putting in troublesome feedstocks to use them as fuel for power generation. But increasingly we see that there are lots of components coming out of a gasifier which are actually of interest as they are as such for the chemical industry. Green BTX, for example. So these are also things we can study with our tools and methods. So a quick summary about what's going on at Chalmers. We're doing a lot of conceptual design and process integration studies, looking into these decarbonization solutions. We're interested in identifying opportunities for implementing new energy-related technologies in such systems, and there we need a lot of input from our fellow research groups within the ECE profile, and we also need to work a lot about these long-term assessments for seeing the impact of those technologies. A few take-home messages just to finish up. So energy efficiency is a lot more than duct tape and putting in low watt bulbs. It's a very important tool for developing decarbonized processes. Lots of potential out there. Even more potential if we take a broader system perspective. A lot of work done about energy efficiency potentials doesn't really take into account the impact of new future technologies, and even less, and that's the major challenge, the interplay between many new technologies being implemented, or maybe not at the same time, but in some point in the future. So we really need to take into account interplay between things which don't exist or at very much the initial development stages. And the most important thing also, energy efficiency, the big gains usually be made by doing major changes, and that can only be done if it's done at the same time as other strategic investments. And that's the big challenge for us working with energy efficiency, is we're kind of add-ons to other bigger projects, and when people are thinking about other bigger projects, they're mostly interested in the big project and not the side projects, which also have a big potential. But that's the challenge, but that's also the opportunity. So the light just went off, so thank you. All right, thank you for your attention.